Okay, so I'm going to tell you about how we're building molecular computers in our new group here in Maynooth. This work involves several different disciplines. We're just two in the group for now, but it involves a wide range of disciplines from computer science, we're both computer scientists, to actual chemistry. So this is our examples of molecules we can build. One main challenge when you work at nanoscale with molecules is that we don't have tools to actually grab the molecules and put them together. And unlike in traditional fabrication processes where we take matter and carve it or remove matter, here we're forced to work in different ways using different construction paradigms, such as self-organization and self-assembly. So the only way to work at nanoscale, work with molecules, is to program molecules so that they self-assemble into whatever we want. So we can build a variety of things from the shapes you saw in the previous slide to circuits. Such as this one, which is a binary counter, so it counts in binary. Here, this is a microscope image, and the AFM atomic force microscope image of this process going here, counting binary from 1, 2, 3, 4, etc. And where the zeros and the ones here are represented by these tiny molecules in white. So our main model, since we're computer scientists, our main model to study and work with these things is called tile assembly, and it's very simple. It's just based on square tiles. I've already done this talk in front of 10-year-old school kids, and they were fine with it and play with the model. So it works by we work with these square tiles with colors in their borders, and the assembly rules are extremely simple. It's just that if at least one side matches, if you have the same colors, you start with a finite set of tile types and an infinite supply of each tile type. And at each step, you're free to add a tile if at least one color, one side matches in colors. Like for instance, here we can build these assemblies like one tile at a time. So this is very simple, isn't it? So we're a little mismatches. For instance, it's not forced that all tiles will always agree on all borders, but as long as one tile matches, it's fine. Like here, for instance, we've got a mismatch. There's an orange glue here and a blue glue here, so they mismatch. But that's allowed, it's fine. As long as one side matches here, that's okay. And so the challenge, so we can actually implement these things with molecules. And one of the challenges we have when we try to use that program is that sometimes it doesn't quite do what we want. And since we have no tools and we don't actually grab matter, we're forced to play with it. So for instance here, when you have a repeated tile type, you can look at the path between them and copy it again forever. Because the rules of the assembly are the same everywhere, right? And so this is really bad. For instance, if you're working in the lab and you have this molecules in the test tube, well, if it grows infinite and eats up all your DNA, all your molecules, then you're basically fucked. You cannot do anything with it. So you cannot even image it. So the thing is, sometimes you can be more clever and actually use repeated tile types like here to block this from happening. So now the main questions we might look at on this model are, for instance, can you use these blockers, these blocking mechanisms to program things, to program useful things? And other very simple questions that, again, I've submitted to school kids is like, for instance, what's the minimum number of tile types required to build an n times n square? If I give you a number n, can you design a tile type that builds a square of size n times n? That's still an open question in the field. Actually, many very smart people have looked at it and they failed to solve that. It's very simple to state, right? Another thing you can look at is what's the longest non-pumpable, that is the longest assembly that cannot be made into an infinite thing by using blockers, for instance. So these are really fundamental questions that might unlock very fundamental mechanisms to allow us to work in the wet lab, which is something we already do with other kinds of molecules and other kinds of mechanisms. All right, so that's my talk. Thanks.